Hi guys, I'm Vicky, your science tutor, and today we're exploring the reactivity of metals. So if you've ever wondered why some metals rust, some fizz in acids, and others just seem totally unbothered, it all comes down to their reactivity. So in this session we're going to have a look at the reactivity series and what makes some metals more reactive than others, why this matters in real life, and we're going to have a look at some of the practical methods that we can do to determine a reactivity of a metal. Okay, so let's get started. So here we've got then a section of the reactivity series. Now depending where you look for a reactivity series, whether you use Google, look in exam books, textbooks, revision guides, you're going to see a slightly different variation. But they all sort of got the same pattern, that up at the top we've got the most reactive metals and down at the bottom we've got the least reactive metals. So the reactivity series tells you how reactive a metal is compared to another, and it's quite useful in being able to predict how these metals are likely to react. And as we go through a sequence of slides today, what you'll see is that some of these things we've already encountered. So we're going to have a look at how metals react with acids. We've already looked at metals with acids in an earlier video. We're going to look at metals with water. If you think about group 1, we determine their reactivity by looking at how they react with water. And we're going to have a look at how we can use displacement reactions to determine reactivity. And that links to our group 7, because we use displacement reactions with group 7 to determine their reactivity. So I know group 7 are not metals, but we can use the same principles. Okay, so as I was saying, reactivity series is a list of metals that are arranged in order of how reactive they are. We've got the most reactive up at the top and we've got the least reactive at the bottom. Now some of these will be familiar with you because here you've got the group 1 metals and group 2. You know that they are reactive. And when we looked at group 1 metals in the session, group 1 metals, we went on to explain why they are more reactive. So group 1 become more reactive as they go down the group. And that's because it is more easy for the lower ones to lose their outer electrons. And as I've said to you before, reactivity is all about how easily gained or lost electrons are. Electron structure dictates reactivity. So if we're thinking, because today we're thinking just about the metals, we know that metals always lose electrons, and therefore the reactivity of a metal is derived from how easily or how difficult it is for that metal to lose the electron. Okay, so let's just make a little note of that. So reactivity is derived from how easily, if we say how easily it forms metal ions, or forms the positive ions because they're losing the electrons. Oops, spell it right, that'd be handy. It's because my next word was going to be it. Okay, so from that sentence then we know that metals lose electrons, therefore they will become positive ions, and it's about how easily that forms. Now when we studied group 1 and we talked about their reactivity, they become more reactive as we go down the group because the outer shell electron is further from that nucleus and has more shielding. And so we can easily look at a metal and already get some idea and have an idea about how reactive we think it's going to be based on number of electrons in the outer shell, how far down it is a group, etc, etc. Now you will see on the reactivity series there is usually carbon and hydrogen labelled on there. They are not metals, they're there as reference points, because in some cases when we talk about extraction of metals we need to know how reactive they are in comparison to carbon, and when we look at electrolysis of metals it's about how reactive those metals are in comparison to hydrogen. So those two are often listed on it just as those reference points, not that they are metals. Okay, so how can we find the order of reactivity then? So one of the easiest ways would be very similar to our group one where we react them with water, but if we've got some metals, so like here you can see we've got zinc and iron, they are less reactive than the group 1 metals. So simply putting those in water, well, iron would eventually rust with water, but that's a very slow process. So if we react them with with acids, we just get a faster reaction so that we can actually kind of see what's going on. We get it in a bit more of a reasonable time frame. So the first thing we could do is we could simply just react them with acids, and we could monitor the amount of bubbles that would be produced. You can see from that little diagram that magnesium is the most reactive because it's producing the most bubbles, and iron is the least reactive because it's producing the least bubbles. And in some questions you get a little diagram like that and you are asked to order the metals in their reactivity. In this case it would be magnesium, zinc, iron. So that's one way that we can look at them. Now, when we get into some of the even less reactive metals, such as copper, even when we put those into acid, the reaction is going to be so slow that in terms of doing a practical in a lab to deduce this reactivity, it's going to be too slow. You might get the odd bubble from it. Okay, so there are other ways that we can test that reactivity as well. So one, we could just observe and we could simply look at, well, that's producing the most bubbles, therefore that must be the most reactive. Another way, and quite a common exam question, is to measure the change in temperature. And measuring that change in temperature might just be that little bit more accuracy that we need rather than just simply monitoring the number of bubbles. If you've just got a few metals, that works okay, but if we had, say, more metals that were in group 2, so say we had magnesium and calcium, their reactivity might be pretty similar, and so simply observing the number of bubbles might not be enough to be able to say yes, magnesium is more reactive than the calcium, or calcium is more reactive than magnesium. Just while it's in my mind here, because you can see we've got another sort of what we call a quantitative test, is that you can see we're using the squeaky pop test. This is a great opportunity when we're talking about reactions of metal with acids for examiners to drop in gas tests. How do you test for hydrogen? We use the squeaky pop test. Now it could be that you test the hydrogen being produced, and there you can see we've just got loud squeaky pop, a squeaky pop, and a muted squeaky pop. But it's all other bits of evidence that would help you to order their reactivity. The second method then, again, that we have already covered in terms of what a displacement reaction is when we looked at group 7. Yes, they are not metals, but the principle of it is the same. So in a displacement reaction, a more reactive metal will displace a less reactive metal. I'm just going to budge these down. I stole these because they were nice and colour coordinated, which makes it easy to see where things are moving from and to. But let's just make a note that in a displacement reaction, a more reactive metal will displace a less reactive metal from its compound. Okay, so if we have a look at these then, so here we've got iron and we're reacting it with copper sulfate. So if it is more reactive, it will displace the less reactive metal from its compound. It's basically going to go along and it's going to pinch the second part of the compound. So if we look here, we've got iron reacting with copper sulfate that then produces iron sulfate, and copper is kicked out on its own. Therefore we can say here that iron must be more reactive than the copper because it's kicked it out. In the second reaction, we've got zinc with iron sulfate. Well, zinc now displaces the iron because it becomes zinc sulfate, and iron ends up on its own. So just by completing these reactions, we can deduce which is the most reactive, because if we think about it, from the first one we know that iron was more reactive than the copper because it booted the copper out, but then when we reacted iron and zinc together, zinc kicked out the iron, therefore the zinc must be more reactive than the iron. So by completing these series of reactions, we can work out which is the most reactive. Now, in displacement reactions, what we're doing is we usually see these different coloured precipitates. So we can see that we had a blue solution. So when we've got copper sulfate, this copper sulfate solution is blue, and the iron sulfate has a clearer solution. And you can see that the copper is now built up on that piece of iron that we've put in, and the solution has changed colour. So colour changes often come along with displacement reactions, and that's what we looked at when we looked at group 7. We could see those colour changes that were indicating that a reaction has happened. So when you're thinking about these reactions, you've got to think about, well, what do I know about reactions? How do I know if a reaction is happening? Am I seeing bubbles? Am I seeing colour changes? Am I getting a temperature rise? And as I said, a probably slightly more accurate way would be to measure the temperature change. And in exam questions you see a lot of these with temperature changes. You're given the table of data, and we're going to see some examples of this in a minute. You see the tables of data with the temperature change, and you again just have to deduce the order of their reactivity based on that temperature change. Okay, so let's have a look what it's going to look like then in an exam question. So this is a lower level question. This is one of the most basic, straightforward types of measuring reactivity. So here we've got 4 metals, A, B, C and D, into hydrochloric acid, and it shows us the bubbles in each tube. And all we've got to do is use figure 1 to answer part A and B. So it says which metal is copper. Well, we know from our reactivity series that copper's down at the bottom, it's very unreactive, so that's going to be B because it isn't producing any bubbles. And which metal is the most reactive? Well, the one that's most reactive is the one that's producing the most bubbles, and therefore that's going to be C. So questions can be as simple and as straightforward as that. Okay, if we're moving it up slightly, So here we've got an example of using displacement reactions. It doesn't go into any colour changes, it simply shows, do they react or not? So did a displacement reaction take place? And so we've got to put them in order of their reactivity. So where we've got a tick, a displacement reaction did take place, and where we've got a cross, it did not. So let's have a look at what we've got. A has got 1 tick, B has got 2 ticks. Let's just write that down. 1 tick, 2 ticks, C's got 0 ticks, and D has got 3. So whatever C is, it didn't manage to displace any of those metals from their compounds. So I would say that C is the least reactive. And just be careful there, I nearly made that mistake. Just be careful whether it wants the most reactive at the top or the least reactive at the top. Yeah, which way around it is. I nearly put C as the most reactive then. If you did that in an exam and you got them in the right order but the wrong way around, you would gain a mark because you've still kind of shown your analytical skills, but you wouldn't get the full marks because it's just not right. It's not that C is the most reactive. Okay, so if we go from C, 1 reaction then was A, 2 reactions was B, and D had 3 reactions, therefore it was the most reactive. Okay, so again, typical questions, it is just analysing, checking your analytical skills. Can you use that information to deduce that reactivity? Okay. So here we've got another example. This is using the temperature increase in a reaction. Excuse me. So we've got a little bit of a method. So we've got hydrochloric acid and we're adding a spatula of metal powder. So we're using the metal powders, increased surface area will react faster. And then we're measuring the highest temperature the reaction mixture reaches. Okay, now in the first question, I think in part A you were asked to calculate the mean temperature increase of magnesium. Okay, but it's not essential. It's going to be around 50, isn't it? Okay, the temperature differences are so big that we can quite easily see what we need to work it out. So determine the order of reactivity using the table. So the one with the highest temperature change is going to be the most reactive. Therefore the most reactive is going to be magnesium. The lowest temperature change was cobalt. And therefore in the middle we're going to have zinc. Okay, so it could be a series of displacement reactions or a series of temperature changes, and you have to deduce their reactivity. Okay, so in this one we've got a similar idea. We've got temperature changes, but what we're going to do here is it then asks us to kind of expand a little bit on this question. So why was there no temperature change when silver was added to it? So it's expanding that knowledge of, well, why did silver not do anything? It's because it's unreactive, but we'll get there, we'll have a look in a second. So here we've got a set of displacement reactions and they've measured the temperature change for each metal. So use the results to work out which metal is the most reactive. That's going to be the one with the highest temperature change. So the most reactive metal is magnesium. Why? At the highest temperature change. Now if you just use your knowledge about what you know about metals, etc., if there was something in group 1, we know that they're really quite reactive, and group 2 are similar to group 1, they're metals, they've just got 2 electrons in their outside shell, so they quite easily give those up. So anything that is in group 2, like magnesium, is probably going to give a high level of reaction. Ones that are least reactive, we tend to always find copper. That's why we use it in lots of pipes and things, water pipes in your house, because it's unreactive. So we've got like copper, silver, gold, platinum. They're our most unreactive. So like here where we can see gold and silver, we got no temperature change because we know those are unreactive. We use silver and gold in jewellery because it's unreactive. It's not going to react with the oils on our skin. We're not going to get caught out in the rain and suddenly start fizzing and popping. So we choose metals for their uses, sometimes based on their reactivity. Okay, so the next part of this question says explain why there was no temperature change when silver metal was added to the copper sulfate solution. Okay, so let's have a look at how we write the answer to that. So here, 2 marks available. Why there was no temperature change, so we're going to say that silver did not react. Okay, or we could say silver did not displace the copper from the copper sulfate solution, and explain why. Because silver has low reactivity, isn't very reactive, however you word it. So we're identifying that we've got no temperature change because it didn't react. Why? Because it's unreactive. Okay. Following on from this question then, it says it is not possible to put all 6 metals in order of reactivity using these results. Suggest how you could change the experiment to put all 6 metals in order of reactivity. So here, this is because this gold and the silver both give us 0 temperature change. So we've got no data, we've got no evidence for us to be able to put those in order. Okay, so we've got to think about, well, what could we change so that we can actually now order the gold and the silver? Okay, so what we need to do then, because we're reacting these with copper sulfate, is basically we need to replace that copper sulfate with something that is less reactive than the silver or the gold, or at least is less reactive than silver, because then we would have a reading for silver and no reading for gold, and therefore we can put those in order. So what would we change? We need 1 mark, we need some idea about we need to replace the copper sulfate, and we want it with something less reactive than silver. Because if we can produce a reaction, we can get a temperature change, and then we've got some data to, draw up a conclusion. Okay, and the final thing that you could get asked is you could be asked to kind of deduce or come up with a bit of a method to work out how reactive metals are in comparison to one another. So if we have a look at this one, it says we want to know the reactivity of metal Q, so how metal Q, what its reactivity is compared to zinc. Now it tells us that both metals are more reactive than silver. What have we got? We've got silver nitrate solution. So if we react these with silver nitrate solution, we're going to get a reaction. They're both going to displace that silver, therefore we're going to get a chemical reaction happening. So what else have we got? We've got a thermometer. So we could react them both with the silver nitrate solution and measure the temperature change. Okay. It says describe a method they could use. your method should give valid results. A valid result means that we must be able to work out if metal Q is more reactive than zinc, so we can put them in order. Okay, we've got our two metals, we've got our silver nitrate solution, so what are we going to do? Okay, so what we can do is add each metal to the same volume of silver nitrate, and we can measure the temperature change or measure the temperature increase. And the highest temperature change means that it's more reactive. Okay, and in terms of marks, it's 1 mark for identifying that we're going to add each metal, so we've got to react them both. Second mark is that we're going to add them to the same volume of silver nitrate, because if we use a different volume or we use a different mass of the powder, we're not going to have a fair test. Third mark is for identifying we're going to measure the temperature increase, and then the final mark is for identifying that a higher temperature change means that it is more reactive. Okay, now just to wrap up then, so I've just come back to the reactivity series. How is this useful? What do we use it for? Well, as I said to you previously, you'll come across this in a number of different situations. When we talk about metal extraction, yeah, we need to know that, for example, that these mid-reactive ones are extracted by reduction. Yeah, so when we talk about extraction of metals, you'll come back to your reactivity series to check, you know, which are most reactive. Can I extract them using carbon? The ones that are above carbon, we come across these when we look at electrolysis. So in a few lessons time, when you look at electrolysis, again, you're going to need to come back to this reactivity series to know, well, is it more reactive than the hydrogen is more what we compare it to rather than the carbon. But because they're more reactive, we can extract them by reduction, and therefore we have to extract them using electrolysis. Yeah, so the reactivity series is really quite a useful little table and gives us lots of ideas about what reactions will occur, won't occur, and what do we need to do with them. Okay then guys, I hope you found that useful, and as always, if you do need further support, please do reach out to me. Otherwise, I'll see you next time.